Hello everybody, and it's freezing cold in my workshop. It's presently 9.6 degrees centigrade, about 50 Fahrenheit or a bit less. I've had the heating on an hour, so I won't be out here very long. But so somebody asked me on the comments on one of my videos, what do I use for combining two signals together, or splitting a single signal into two. And that was when I was using two RF signal generators, and I was combining the output into a single signal. So I basically use an RF splitter like the ones I've got in front of me, or combiner, and I've got several here which I made, and this is one I made several years ago. In fact, it's got the date on it. See, where did I write it? I'm sure I wrote the date on it. No, I didn't. Oh well, never mind. Not on that one. This is the one that's got the date on it, maybe? No. But anyway, that's beside the point. I made this about 30 something years ago. And you've got a single common input and two outputs if you're using it as a splitter. So the typical application would be, if you had a TV signal and you wanted to divide it and have two outputs to feed two televisions in different rooms, and here's one I made for that purpose, and it's got the old TV connectors on it, which were called Bellingly connectors. So you'd have, this one's labelled aerial, you plug the aerial into that one, and then you'd feed one cable off to one TV and another cable off to another TV. Of course, nothing is perfect and you get some loss, and you can probably tolerate that in if you've got a strong enough TV signal, or if you've got an amplifier feeding the splitter. So you've got two types of these anyway. One is the inductive splitter, which is the one I use, and got a common input and a transformer and two outputs. And if all things in life were perfect, you would get exactly 3 dBs loss between the common and each output, because it's half the power basically. And then you've got the other one, which is the resistive splitter, and I've forgotten how these work, so I got it wrong the first time when I was drawing it. You actually have 3 resistors in the star, and this is more lossy. This is 6 dB in the perfect world between the common and the outputs. So I don't bother with those. I use the transformer one, inductive. And the core that I use, where I can find it, is this little, put it on the table. It's a binocular, so called because it looks like a pair of binoculars, core. It's some sort of ferrite or iron dust material with 2 holes in it, and if I zoom out again, that's basically how it's wound. You've got one port, and the wire goes in through the middle of the core, and single turn basically, and then it's tapped in the centre. That's the common. Then it continues round again for another turn, and then you've got the other output, second output. So that's how they're wound. And just for demonstration, I suppose I could try winding one. So get your piece of enamel wire, feed it through, and that's one port on that side. Goes through a second time through there. Right, so now it's gone through approximately one turn, and this the tapping point for the common will be here. If you like, I can just do that with it. And then, oh, this bloody camera. Right, so then you feed it through another one. And I know it looks a bit rough, but I'm not going to use it. I'm just trying to demonstrate. So then it goes through another one like that. And now you've got a very simple inductive splitter. And you've got your 2 ports and your centre common, and that's that. So if I open up this one, which has got a little brass plate in the middle, and I sort of made all this out of a solid block of brass, and I etched it with ferrite chloride to indicate which was effectively the input in this application and the 2 outputs, and it's held that plate in there. Oh, there's the date on it. I made that on the 11th of the 8th 1988, so it's quite an old piece of old project. So get rid of that, and you can see the transformer, binocular cord transformer inside. So that's that really, and I'll put that back in and tighten up the little grub screw. And that's one I just generally use in the workshop. If I want to combine 2 signal generators, I put them in what are labelled the outputs, and then you get a combined signal at the output, what was labelled the input on this one. It's the common connection, and of course you get a 3 dBs between these 2 ports and those 2 ports. And similarly, that's the other one I made a few years ago. It's exactly the same, and this one I had in the garage, so it's been fairly damp in there and it's got a bit corroded. And this one I had, which was taking an FM aerial signal which had been amplified and splitting it into 2, and one cable was feeding into the kitchen and one was feeding into the lounge, so it was just splitting that amplified FM signal off the outside aerial. So there you go, that's that one. And of course there was this one which I had at my parents' house for my parents to feed 2 TVs in different rooms, which is actually the same design. So now we'll look at it on the spectrum analyzer and we'll see the response of these devices. As I said, ideally you get 3 dBs between the ports and the common, but in practice you don't get that, of course, because nothing's perfect unless you're somebody like Hewlett Packard or Mini Circuits, who make these at a professional level. You'll get much better results than I will. But anyway, we'll hook one up to spectrum analyzer and we'll look at it on there. So what I've done is I've got the spectrum analyzer wired up with its tracking generator output going to the input, and just a through connection at the moment, so we can get a response of the device and the test. And I'm sweeping between 1 megahertz and 2 gigahertz just because I can, although normally I wouldn't use one of these splitters, combiners, higher than probably a few hundred megahertz. So I've got to make sure all my connectors are decently tightened up, and I think I'll renormalize it. So there we go, we've got a nice flat. Ah dear, shouldn't have done that. Yeah, a nice flat line, and I set the vertical scale to 5 dB per division, so we get a better resolution when I do the tests. So now what I'll do is I'll take this little thing here and I'll connect the output from the tracking generator to this common port. And the important thing is, when you do tests like this, is you have to terminate all the ports, otherwise you'll get a funny response. So I have to put a 50 ohm load on the unused port, which is what I've done. So that's going in there, that's coming out one of the ports, and 50 ohms on the other one. And if we look at the screen, as you can see, it's rather wiggly. Well, as I said, it's nothing's perfect when you build it like that at home, and it's good enough for what I want. But if we go right down here, you know, it's reading 3.7 dB at 27 megahertz, and it goes surprisingly quite low. You get to 1 megahertz and I don't think it can read very well down that far, but so it's fairly usable from fairly low frequencies. And if I press peak, in fact, see what the lowest is. So 550 megahertz, I'm getting exactly 3 dB loss, which is the best it's going to work at, it seems. And that's just probably due to stray capacitance and stuff in the brass box. And some of its worst frequencies are at 646, it's dropped to 4.27 dBs of loss. And I mean, if I swap these over, it should be exactly the same in theory, because it's all symmetrical. Yeah, we get more or less the same, 4 point whatever. And as I said, I don't need it to go that high in frequency. I mean, 1 gigahertz, it's 3.5 dB, so that's not too bad. And we can go all the way up, 4.6 at 1.5 gigahertz, and it works fairly well up to 2 gigahertz, so that's good. So there you go, that's looking at the response. And of course, these two ports should be fairly well isolated, but we can check that as well by feeding a signal into one of the ports, the output ports in this case, terminating the input with 50 ohm, and then measuring at the other port. And that's the isolation there between the two ports. As you can see, it gets a lot worse at higher frequencies. It's down to 13 dB, and the best it seems to be is down the low end. Well, at 1 gigahertz we've got 17 dBs of isolation, which is not perfect, but I suppose it's good enough. But if you go right down to 83 megahertz is 22 dBs of isolation. If I disconnect the load, it makes a fair difference, doesn't it, if you don't terminate it properly. And I imagine it will do the same in its normal operation. If I put the signal back into the input, terminate that, and take this, now unterminate one side, it does affect it quite considerably. In fact, yeah, so 83 megahertz, I've now got -5 dBs of insertion loss with an unterminated port. So there we are then. What else can I say about these devices? Probably not a lot, but they work fairly well and they're easy enough to build, and you can get fairly good results as a home constructor. So there we go then. So thanks for watching, and bye for now.